I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on capacitors in a circuit set up in parallel, series, or a combination of those capacitors in a circuit. So in this series of videos, we're going to talk about electrical circuits, which is current, resistance, potential, and electrical power. So what we're going to start with, though, is capacitors, where we left off with the last set of videos. We're going to talk about capacitors in a circuit when they're set up in series and parallel, and also combinations of those. So first, let's talk about capacitor setup in a circuit. So we've seen where we've had a single capacitor hooked up to a source of potential, and we know that the charge is moved off the positive plate through the battery onto the negative plate, and each of the plates have the same amount of charge. Now, what we're going to do is we're going to look at multiple capacitors hooked up. So we're going to add two more capacitors. We're going to connect those capacitors with wires, and then we're going to connect the capacitors to the battery. Now we know what happens is that on that positive plate where that's connected to the positive end of the battery, the charge moves off of that positive plate through the battery and it goes to the plate attached to the negative. So that makes each of those have a equal charge, just opposite sign. Now what happens is then that charge polarizes the plate across from it, moving electrons off, causing that plate to have a positive charge that's equal to the charge that was on the original positive plate, making the plate negative that is closest to that. Well, then it polarizes that plate, moving negative charge off of that plate, making it a positive Q charge, and then the last plate becomes negatively charged. So all plates have the same charge value when the capacitors are set up like this, and the value of the charge that's moved is equal to the charge that's moved off the original positive plate, the one that's connected to the battery. Now, if we disconnect those from the battery, the charge is going to remain. So we can hook up a wire to each side of the capacitors and discharge them, as you can see there. Now, what actually happens is when we hook them up, they charge instantaneously. So there's minimal resistance in the wire, so the charge is going to move very rapidly. And remember, the total potential across those capacitors is equal to the total potential of the battery. These are capacitors that are set up in series because there's only one path for the charge to take. So if you trace your finger from the positive end of the battery and move it through, there's only one path. That's how you know that capacitors are set up in series. Now, we're going to simplify the diagram with something called a schematic diagram. Schematic means that they're schema or symbols that represent things within the diagram. So we're going to draw symbols that represents each individual component of our circuit. So first, we're going to start with the battery. The battery is represented with a long line and a short line. The long line represents the positive end of the battery, and the short line represents the negative side of the battery. Then what we're going to do is we're going to draw straight lines with right angles to represent the wires. And then a capacitor, this is known as a parallel plate capacitor, so we draw parallel lines to represent the capacitors. Now, this is one way to represent the capacitor. We can also represent it with a line and a curved line. That would also be a capacitor. But what we're going to look at and use most frequently is the parallel lines. And then we connect those with the wires, and those are also straight lines. So this is a schematic diagram of C1, C2, and C3, three different capacitors hooked up in a series circuit. Now, each of them having a different capacitance means that they each have a different potential that's measured across each of those plates. So delta V1 through delta V3 for each of the three capacitors is what's being measured as the capacitors are fully charged. And the battery has a potential difference measured as delta V, is that's what we'll label the potential for the battery. Now, what we're going to do is we're going to talk about equivalent capacitance. So what equivalent capacitance is those three capacitors set up in series are equivalent to setting up a single capacitor by itself in a circuit. So we're going to learn how to calculate the equivalent capacitance of a series circuit. So we're going to start by using the capacitance equation, which is C is equal to Q divided by delta V. And we're going to rearrange this for delta V is equal to Q divided by C. Now, the delta V in the circuit is going to be the total potential that's measured across the capacitors is going to be the sum of the capacitor's potential that's being read once they're fully charged. And that's going to equal the total potential of the battery, as we know that once capacitors are fully charged, the potential across the battery is equal to the potential read across the capacitors. So we can substitute Q over C, and that's going to be the equivalent capacitance. And then we can substitute each of them for Q over C1 plus Q over C2 plus Q over C3, just substituting in the potential value of each of those capacitors. Now, what we know is that the charge on each of the capacitors is equal, so we can cancel out the charge, leaving us with only values of capacitance. 1 over the equivalent capacitance equals the inverse of each of the individual capacitors added together. Now we can simplify this and say that it's 1 over the equivalent capacitance is equal to the sum of the inverse of the individual capacitors, and that is the equivalent capacitance in series. That's why the EQ comma S. So to find the equivalent capacitance in series, you add up the inverse of each of them. Now remember, this isn't the equivalent capacitance, that's the inverse of the equivalent capacitance. So the last thing that you would have to do is flip the value that you get to find the equivalent capacitance. So this equation is used to calculate the equivalent capacitance in a series circuit. The CEQS, that just stands for equivalent capacitance of a series, and CI stands for the value of the individual capacitors. Now let's look at a situation where they're all set up in parallel. So what does parallel mean? So we're going to connect each of the individual capacitors with their own wire and then attach all those wires together and then attach them to the battery. So setting them up like this is almost like just having them connected directly to the battery without any other capacitor. So what happens is that that negative charge moves off of that positive plate through the battery and onto the negative plate. And that's going to do that for each of the individual capacitors. The positive plate becomes positively charged by moving negatives to the other side. So all three plates are going to have the same potential measured across it, because it's like they're just hooked up to the battery by themselves when they're set up in parallel. So we're going to label those C1, C2, and C3. The delta V is going to be the potential measured across the battery, and each of those potentials is going to be the same across the capacitors when they're set up in parallels. And so now we're going to look at a schematic diagram. We know the battery is a long line for positive and short line for negative. And then we have our wires. Now we're going to add additional wires with those parallel plate capacitors set up in parallel. So we have C1, C2, C3. So this would be the schematic diagram for three capacitors that are hooked up in parallel. Now let's learn how to calculate the equivalent capacitance in parallel. So remember, equivalent capacitance just means if I set one capacitor in the circuit, it would be equivalent to the same value as the three capacitors in parallel. So we're going to start with our equation for capacitance. And what we know is that the total charge that is moved is going to be equal to the sum of all the charge that's moved off of each individual capacitor. Unlike a series where the charge is equal on each, in parallel, they're different because they're directly connected to the battery. So we're going to rearrange our capacitance equation, and we're going to solve for Q. So delta V times the capacitance is equal to Q. So we can substitute that in for each of the individual values. So the total charge that's moved is delta V times the equivalent capacitance, and then delta V times C1 plus delta V C2 plus delta V C3. And what we know is that each of those delta V's is going to be the same as the battery, so we can simplify that and we can cancel out all of the delta V's. So that leaves us with an equation of only capacitance in the equation. So the equivalent capacitance is equal to the sum of each of the individual capacitors. So we can simplify that. The capacitance equivalent in parallel is equal to the sum of the individual capacitors. So in a series circuit, we have capacitors set up with only one path to take from the battery through to the negative side of the battery, and three different capacitors each are going to measure three different change in potentials across those plates. They'll have the same charge, but different capacitance means a different potential difference measured across each, but the sum of those adds up to the total potential of the battery. And remember, charge is equal on all of the capacitors. And the equation to calculate the equivalent capacitance is the inverse of the equivalent capacitance in series is equal to the sum of the inverse of the individual capacitors. Now, in a parallel circuit, the capacitors are set up in parallel. It means that there's multiple paths that the charge can take. So we're moving charge off of each of the individual capacitors through the battery. And if they have different values, that means the charge is going to be different on each of the capacitors. But the potential difference is what's the same. So to calculate the equivalent capacitance in parallel, we just simply add the values of the capacitors together. So let's look at an example problem. So we have a 48-volt battery with 3 capacitors set up as you see here. The values of those capacitors are given, and we're going to find 3 different things. We're going to first find the equivalent capacitance. After we find the equivalent capacitance, we're going to find the charge that's moved onto each capacitor. And then finally, we're going to find the potential difference that's measured across each of the capacitors. So finding the equivalent capacitance. So we're going to diagnose the circuit, and we can see that the 5 and the 4 microfarad, those are set up in parallel with each other. So what we're going to do is we're going to look at the parallel equation first. So we know in parallel, we just sum the individual values. So we can just add up C1 and C2, or 5 microfarads plus 4 microfarads. That's going to give us 9 microfarads. And I recommend at this point then redrawing the circuit and drawing it with an equivalent capacitor of 9 microfarads, because that's what equivalent capacitance means, is those two are equivalent to one singular 9 microfarad. So now we have 2 that are in series, so we're going to use the series equation, 1 over C1 plus 1 over C2. So we have 1 over 9 microfarads plus 1 over 3 microfarads, and that's going to give us the 4 divided by 9 microfarads. Now microfarads is in the denominator, which we need it to be in the numerator, so we just flip both sides of the equation, and that's going to give us 9 microfarads divided by 4, or 2.25 microfarads. So that's like saying all 3 of those capacitors set up is equivalent to one singular 2.25 microfarad capacitor. So we're going to start with this drawing to help us find the charge that's moved off of each capacitor. So the first thing is we're using that equivalent capacitance is we're going to find the total charge moved. So we know the equivalent capacitance is equal to Q divided by delta V. And looking at our circuit diagram, we know that if we're trying to find charge, we can rearrange the equation. We know delta V is 48. We know the equivalent capacitance is 2.25. So we can rearrange that equation to solve for Q. Substituting in the values, we get 108 microcoulombs of charge total that's moved off of the capacitors to the battery. Now, if we move and draw back the diagram with just 2 series, that means each of those in series has the same charge. Remember, in series, they have the same amount of charge that is moved because it's moved from the left side of the positive plate on the 9 microfarad to the negative plate of the 3 microfarad, and then polarizes the 2 plates in between, causing them to have the same charge, just opposite. Now we know that the 9 microfarad, there's 108 microcoulombs, but those values are 2 parallel capacitors. Now what we're going to do is we have to skip around a little bit, and we have to find the potential difference across the parallel capacitors. And we're going to use the equivalent capacitance equation equals Q divided by delta V. Now that equivalent capacitance, we know, is going to be the equivalent capacitance of the parallel circuit. That's the 9 microfarads. And then we know there's 108 microcoulombs of charge moved across the plates. So we're going to rearrange our equation, solve for delta V, and 108 microcoulombs divided by 9 microfarads is going to give us 12 volts, which means that the 9 microfarad has 12 volts of potential that is measured across it. So now we're going to find the charge on each capacitor in parallel. So we bring back our original diagram, and we know that each capacitor stores 12 volts of potential across the plates and has a total of 108 microcoulombs of charge moved off of both capacitors. It's not 108 off of each, that's total off of the 2 capacitors combined. So we're going to use our equation Q equals C delta V because we know the capacitance and the potential difference. So 5 microfarads times 12 volts gives us 60 microcoulombs. That's the amount of charge that's on the 5 microcoulomb capacitor. And then we can do the same thing for the 4 microfarad capacitor. We get 48 microcoulombs. And if we add 60 microcoulombs plus 48 microcoulombs, well, that gives us a total of 108 microcoulombs, which is how much charge we calculated that would be moved total across the parallel circuit. Now the last thing we're going to do is find the potential difference across each capacitor. Well, we've already done that for the 5 and the 4 microfarad, so now we need to do it for the 3 microfarad. So the 5 and the 4 microfarad each have 12 volts of potential when the battery is hooked up. So now we're going to calculate the 3 microfarad. So we know the capacitance and we know the charge that's moved, so we can use our capacitance equation again. So delta V is equal to Q divided by the equivalent capacitance. The equivalent capacitance in this case is just going to be 3 microfarads because it's only just the singular capacitor. So we take 108 microcoulombs divided by 3 microfarads, and that's going to give us a total of 36 volts that is stored across that parallel plate capacitor. Now there's something interesting that happens is when we take one path from the battery through the one of either the 5 or the 4, we take each of those having 12 volts, so 12 volts plus the 36 volts adds up to the total potential that's measured across the battery. And that will always be the case when you take one path, the total potential that's stored on the capacitors is going to equal the total potential on the batteries. That's why each of the parallel branches each stores 12 volts when completely charged. Let's look at a second example problem. Notice that this one's set up just a little bit different. So we still have a parallel branch and we also have capacitors set up in series, but this time we have the series as one of the branches. So we're going to try to find the equivalent capacitance in this circuit. Now, unlike the previous one where we had 2 that were in parallel and then 1 by itself in series, now we have 2 that are in series, the 6 and 3 microfarad, and that 8 microfarad is in parallel with both of those. So in this case, what we're going to do is we're going to find the equivalent capacitance of that series part first. So we're going to do 1 over C1 plus 1 over C2, so 1 over 6 microfarad plus 1 over 3 microfarads gives us 3 over 6 microfarads. Notice the units are in the denominator, so we have to flip it to find 6 microfarads divided by 3, which gives us 2 microfarads. So now we have 2 capacitors set up in parallel. So now we can use our parallel rules. We can use the capacitance for parallel, which is just adding the 2 values, so 2 microfarads plus 8 microfarads. That means those 3 capacitors set up in parallel and series give us a total equivalent capacitance of 10 microfarads, which is like having one singular 10 microfarad capacitor set up with a 24-volt battery. So this is how you calculate equivalent capacitance. You got to diagnose the circuit, make sure that you find the ones that are set up in series or parallel first. So let's go ahead and recap those 2 example problems. So in a series circuit, we have this equation where we have 1 over the equivalent capacitance in series is the inverse of the sum of the individual capacitors. And in parallel, we have the equivalent capacitance is just the sum of the capacitors. So what we're going to do first is we found the combinations for both. We evaluate the circuit, and if there are 2 or more capacitors in parallel with each other, and then one that's in series, we use the parallel, then the series. Now, when we diagnose the circuit and we determine that there are 2 or more capacitors in series with each other, and then a singular one in parallel with those, we use the series circuit equation first and then the parallel equation. So this was an introduction to capacitors in a circuit. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X at Cavi Coaches.